All right. Like I said, you can turn your homework in. I'll collect them. Cute.
Negative would mean it goes clockwise.
Thank you. Thank you. Thank you. That's okay. I got everything back here? Anybody? Homework? No. Thank you. All right. Ooh, I should have brought a bigger clip. Oh well. All right, I will begin with a word of prayer then. Begin. Dearly Father, we thank you for this day. Again, I thank you for these students. Just ask you to just bless our work today. Help us to understand a little bit more about your creation. Help us to glorify you in what we do, Lord. In your name I pray, Lord Jesus. Amen. So, any questions about anything before I get going? No? All right, so let's talk about, so I introduced torque and angular momentum last time, right? And we said, what did we say? We said that for a point mass, oh man, what the? Ah. Where is it? There's a big one. Ah. So for a mass m, you have angular momentum is equal to mass times its position cross its velocity, right? mr cross v. Of course, you could bring the m into that, and you can just write it also as r cross p, right? Where, as usual, the momentum is the mass times the velocity. We discussed that if you calculate the time rate of change of the angular momentum, what we worked out was that you got r cross f, where f is the net force, right? So for a single mass, if the net force applied is, if it has no piece which is perpendicular to the radial arm, then the angular momentum is going to stay constant, right? So, or in other words, if this is, we define this to be torque, right? This is the torque, tau, the net torque, if you will. And so if the net torque is 0, then the angular momentum is conserved for a single mass, right? But what if you've got a bunch of masses? So what if you have a system? So we could call this a rigid body, or some system of masses. So I don't know what that looks like exactly, but you can envision, here's M1, here's M2, here's M3, and I'll just do 3 in my picture, but think about n masses. All right, see a whole bunch of them, and each one of these masses, what's going on? Well, they've got some some velocity, right? And but more to the point, you can calculate their position vector, r1, r2, right? r3, right? And what do? We figured out we can calculate the center of mass for the system, right? And what did we prove previously? We proved previously that the total mass m is mass 1 plus mass 2 plus plus n masses, right? That was the total mass of the system. What was the formula for the center of mass? R vector, what was that? 1 over m, m1, r1 plus plus mn rn, right? That was our formula for the center of mass for n masses. There was a question on test 2 about this, right? Some of you got it right. And what we proved was that if you look at the mass times big V, and say that that's the net momentum, where big V is equal to dr dt. Well, we had a theorem, and what did our theorem say? Our theorem said that the time rate change, right, of the total momentum for the system is equal to the net force applied, right? How do we calculate the net force? You calculated the sum of the forces, whatever the force was on each constituent mass, and you added them all up, right, for the system as a whole. And we argued that the internal forces, the force of one mass on the other, those canceled out because they come in third law pairs. So I now want to ask a similar question. What's the rotational analog of this story, right? So what if we think about this system altogether and calculate the net torque, right? What's the net torque on this system? Make sure I got everything here. So, so if we calculate the net torque, that would be equal to what? That would be equal to the sum of the torque on the ith one, I equals 1 to n, right? Plus the sum over I and j of the torque on the ijth one. So what I mean by this is so here I'm talking about the torque produced by the net external force on each mass, right? So like, for example, the net external force on mass 1 might be like this, all right? Say that this is F external on 1. So the torque on 1 would be R1 crossed with F external on 1. All right, that would be the net external torque on the first mass. And we can do the same for the rest of them, all right? Now, on the other hand, this ij thing I'm talking about, that's the torque that's coming from internal forces, all right? So internal forces, I'm talking about, there's like maybe there's some force here, right? This is the force of mass 2 on mass 1, right? Well, by third law pair, there's also an equal but opposite force over here of the force of 1 on 2, right? And so I'm attributing the torque that comes from internal forces to this term over here, all right? And so, anyway, so what this gives us then, sum I equals 1 to n tau I. If you think about this, first of all, there's no, the particle doesn't put a force on itself, all right? So like tau I doesn't mean anything. There is no self force on any of these masses, all right? You can only talk about the force of 1 on 2 or 2 on 1. So this sum, you can break up into two pieces. You've got a sum I less than j of tau ij plus the sum over, let's say, j greater than I of tau ij. All right? And what's the formula? So we have the sum over I less than j of like r sub I crossed with f, what's my notation here? R, so j comma I plus the sum over j greater than I of r sub, let's see here, I crossed with f again, ji, I suppose. But the thing is, if you look at this, because of the third law, right? Yep.
It's going to be a dumb question. What's the difference between I less than j and j greater than I?
What's the what?
The difference between I less than j and j greater than I.
Did I write the same thing twice?
Yeah.
Uh-oh. Huh. Let's try this again. I greater than j. There we go. You should be able to see the contrast now, right? There we go. Thank you, sir. So if you look at it with the sum of I and j, does it make sense? There's either terms with I less than j or I greater than j. And then there's also I equals j, but those don't give you anything because the force of any particle on itself is 0. All right. And so, all right, well, the thing, though, is that these are equal but opposite because you can, basically you make a substitution here. I put, I equals to k and j equals to l, something like that. And then this becomes the sum over, k greater than l of r k crossed f j I, which was lk. But this, by the third law, is just minus fkl. All right? And if you look at this, we can rewrite that as L less than K, right? And if you look at that, that's the same as this. Because I have L, so if I could also make the substitution here, it's a very stupid one. I could just let I equals K and J equals L, right? If I do that, this sum is exactly the same as that, but there's a minus, so they cancel. In short, the torque also comes in like equal and opposite pairs because of the structure here. And so, long story short, the net torque is exactly this, all right? And how can I calculate that? Well, I can calculate that. That's the sum, I equals 1 to n. What was tau I? Well, it's the ith position vector crossed with the net external force on the ith one, all right? So that's how to calculate the net torque. Yes, sir?
When you were looking at the two that cancel out,
Yeah.
the I and J, should be reversed.
When I look at the two that canceled out, so what I'm doing is I'm showing that this and that are actually the same sum, but if you look at it, it's minus what the first one is because we have to.
Well, but you have them written as exactly the same with an I greater than J. So does that mean at the F vector, you should be switching the I and J in that equation?
You could do that.
Okay.
Yeah. But the thing is, I want to make this match with that, and I can't ever do that with, I mean, if you want to, you could switch this to minus Fij, and then you could switch I and J. That would be another way to say that they're equal but opposite, sure. Totally agree. Now, all right, so my point to you is that the net torque on this system of masses is that, right? But what else can we calculate here? I think there's something missing in my notes at the moment. Because I want to argue that this net torque is also equal. What would you expect the situation to be here? So the net external force is equal to the time rate change of the total momentum for the system, right? So we would expect that the time rate change of the angular momentum for the system would also be equal to the net torque. That's what I expect. That's what we should expect here, right? So how would you calculate the net angular momentum here? What's the total angular momentum for the system? So, I mean, I'll just put us out of our misery here and just define it to be the sum I equals 1 to n of the angular momentum for the ith mass. All right. So what is the angular momentum for the ith mass? Well, that's what we did last time. And so there, you're just talking about the sum I equals 1 to n of like r sub I crossed with the, as I've explained, the external force. Let's see here. Goodness gracious. External, I'm sorry, I've lost my, golly. Yeah, that's not wrong, that's not right. Sorry, that sneeze, that derailed my mind. That was a powerful sneeze. Let's see here, so good job. So I should have what, momentum there, right? R cross P is the angular momentum. So I should have, like mass, the ith mass times the, ith velocity, right? Where VI is dri dt. All right, let me erase that thing underneath. I'm almost to it, almost to the point here. So what happens? All right, so this is, there you go, that's our total angular momentum. What happens if we differentiate this? What do you get from dl dt here? You get the sum, I equals 1 to n of the time derivative of this guy, right? We worked this out last time. How did this work out? There is something slightly fussy here that I kind of want to gloss over, but let's see here. So this gives me what? I've got VI crossed with MIVI plus RI cross MI DVI dt, right? So the first term is 0, right? Because the velocity is parallel to a scalar ball. I mean, this term is 0, right? That term, on the other hand, this is MA, right? So what are you looking at there? That would be the net force, right? That would be the net force on the ith mass. So what you've got here is the sum, I equals 1 to n, of r sub I crossed with the net force on the ith mass. Now, I think the thing I'm slightly dissatisfied with our current discussion is I know somehow that if there's a piece, if the net force, how can I say this? If the net force on like mass 1, right? It's got two pieces, right? It's got the external force and it's also got the internal force in principle. Somehow we can ignore that internal force. They'll somehow cancel out as we add across all these, So what I'm trying to say is, because we know that the internal forces come in pairs, it follows then that you can reduce this sum just to the following. The external force on the ith one, like that. And that is what we defined to be the net torque, all right? So there you go. So this I have in lecture, I've lost it. But this is in my lecture lecture 30 rather. So like my lecture 30 has that calculation, but it doesn't have this, and I think that's kind of important. So anyway, long story short, if we have a system of masses, you can count on the net force, excuse me, the net torque being equal to the time rate change of the angular momentum, right? So in particular, if the net torque is 0, angular momentum is conserved, right? So let's look at some examples of that. Any questions before I go on, example-wise? Let's see here. So example 1. I like this example here. So suppose you've got like a disk, right? And it's got mass m. Okay, and suppose it's rotating with angular velocity omega, all right? And suppose the disk has radius r, okay? So you've got this disk, it's spinning, right? And then suppose you drop a lump of Play-Doh and it just sticks on the edge, right? Or you could whatever substance you find more humorous than Play-Doh, a bucket of peanut butter. I mean, I don't know. What do you guys want? Peanut butter? An egg? A child? A child made of peanut butter? Or just a child?
A child made of peanut butter.
Is this a regular child or is this an evil child?
It's the evil child.
Evil child? Robot or non-robot?
Yes. Non-robot.
Non-robot? If it's not a robot, then I have to make various inquiries with the ethical board, But just a child made of peanut butter. What's my problem? Okay, fair enough. So you put a child made of peanut butter. And let's suppose the child made of peanut butter has a mass little m. It's chunky peanut butter. Okay, yeah. No? All right. Anyway, so this, whatever you want to call it, it falls, right? And it sticks right here. All right. Then the question, fall, stick. All right. And suppose it sticks at distance, let's say it just sticks at distance r. All right. So r doesn't have to be equal to big R. The question is, what's the angular velocity of the system once it sticks? So what's going to happen? If you think about it, you got if you can imagine you have a record spinning, right? You drop something onto it. What happens to the record? It does what? It slows down, right? So how much does it slow down? Well, so the question is, in this process, is there any torque? See, what I want to do is I want to think about, I guess I didn't fully confess to you either. I said a system of n masses, but what I'm really thinking of is a system of n rigid bodies, each of which has its own angular momentum. So this is just a sort of a heuristic thing to hang our hat on, because I'm really thinking of the disk as a mass, a point mass, which has a particular moment of inertia, and it has a certain amount of angular momentum, just like Mr. Peanut Butter Man there. I'm sorry, child, Peanut Butter Boy, has a certain also angular momentum, right? Is there any torque on this system? I mean, what's making him fall? Gravity, right? What's the direction of gravity? It's down, right? And that would be parallel to the axis of rotation, right? So if it's parallel to the axis of rotation, it's not doing any kind of, there's no torque from gravity, all right? On this system, I don't believe. So just to be clear, this is the rotation axis, okay? Okay, so in other words, we have what we need to conserve angular momentum, right? The net torque is 0, so angular momentum before is equal to angular momentum afterwards. What's the angular momentum of the disk? So we have I disk times omega plus, what's the momentum of inertia for Mr. Peanut Butter Man here? Well, it's little m r squared times his initial angular velocity, which is what? 0, all right? So it gives us nothing. And then what happens afterwards? Well, afterwards, you have the moment of inertia for the disk plus man, right, I'm sorry, plus peanut butter boy, PBB. And then that is times what? Well, times omega f. So just a reminder, angular momentum is equal to, what is it equal to? It's equal to, as a scalar, it's equal to, goodness gracious, curses. L is R cross P. What else can we say it is, though? For a point mass, it is M R cross V, right? So this is for point mass. But for a rigid body, L is equal to I omega. And the direction is what? It's the, the axis of rotation is the direction here. Okay, anyway, so that's what I'm doing. I omega is angular momentum, okay? So what is the momentum? What's the moment of inertia for a disk, right? We worked this out, yeah? Remember? We have 1/2 what? Big M R squared omega is equal to, so this one is what? 1/2 mr squared plus what? So moment of inertia is additive. So you just take the moment of inertia for the disk plus the moment of inertia for the peanut butter boy, which is just a point mass essentially for our consideration. So we have little m times little r squared. That's its moment of inertia. And then you got your final angular velocity, which we're trying to find. And so algebra, there you go. Omega f would be 1/2 m r squared omega divided by 1/2 m big M r squared plus little m r squared. And there you go. Let me show you another, let's do another example here. If I still have time. I think I still have time. Oh, here, I've got some papers. Let me turn these back before I forget. I think some of you are here that weren't here before. Oh, let me put the next example up before I turn the papers back, though. As you guys know, I have trouble making decisions. Let's see here. So another, maybe important's the wrong word. Another example of angular momentum is figure skating. So, so you've seen one of these deals, right? Johnny, or whatever his name is, I need to come up with a name for a figure skater. Pick your favorite name. All right, there he is. All right, he's skating, right? And he's got his arms outstretched. All right, he's got his arms way out, and he's spinning, right? So let's model this. So this let's suppose that he's got arms, and what would be a reasonable mass for the arm? 10 kilograms, 10 kilogram arm. Kind of beefy. I don't know, maybe. All right, so suppose he's got these 10 kilogram arms, right? And he's coming into his move, and he's arms outstretched, and he's rotating at let's say, what's a reasonable rotation rate for a figure skater with arms outstretched? I think 1 radian per second. It's kind of maybe pushing it. That's maybe one radian per second. So suppose he starts out at omega naught equals to 1 radian per second. I guess that's not too unreasonable, right? And then what does he do? He can't change his torso, right? Kind of stuck with that. So his torso is still the same, but he takes his arm and he just wraps them all around his body, right? He just wraps his arms around his body so they're nice and tight. So they have what? They have no, you know, they have no moment of inertia when they're in like that, let's say, right? Negligible moment of inertia. So I guess I need to tell us what would be a reasonable mass for this guy. Let's model the, my picture's deceiving. Let's, all right, to make this more physical, I suppose I can't make his arms just all into a ball. I should model him as a cylinder, right? And so he's got his arms wrapped around the cylinder like a solenoid, all right? And so what's the moment of inertia for a cylinder? Let's say that the mass of his torso is what? I don't know, 40 kilograms? Does that seem reasonable? Is that too little? I'm sorry, I really only know kilograms as they relate to like arm wrestlers. I watch too much arm wrestling on YouTube. So like I'm mostly familiar with like weight classes of various arm wrestlers. It's what I know. So like the ordinary mass for an ordinary human in kilograms, I don't know. I know that what I'm interested in is mostly more than 115 kilograms, but I think for figure skating that's wrong. But if we suppose that the mass is like 40 kilograms and it's a, what's that? Cylinder radius, what would be the radius for a typical torso? Point two? What? What? 0.2? No. Point what? Maybe 0.2 meters? Maybe. 20 centimeters. Is that? It's not unreasonable. It's like 8 inches. So like 16 inches across. Like that's not. Is that normal for a figure skater? Does that even make sense? A question to ask about a figure skater, like normalcy. I don't know. Okay, so my point to you is, before they pull in their arms and do their thing, there is a moment of inertia for their body. It's also rotating, right? And that the body's not going to change, right? So let's see here. What's the moment of inertia before? With the arms outstretched, it's what? It's 1/2 mass of the torso, right? Radius of the torso squared, plus what? With the arms outstretched, what's the moment of inertia for arm outstretched? You're talking about what? Like, essentially, let's assume that the arms are attached in the middle of the torso to make it easier to think about. Okay? What are we talking about? It's a rod, essentially a rod on its end. We figured out it's what, 1/3? Yeah? Is it 1/12?
That's for the.
I think that's for the center. So on its end, I think it's 1/3.
Yeah, 1/3.
1/3. And here we're talking about the 10 kilograms. And I didn't say how long the arms were yet. How long do you guys want the arms to be? 2 feet long. 2 feet long. I take your 2 feet and make it a meter. It serves our purposes. 1 meter. And how many arms does a skater have? 4 arms. Let's give it 2. 2. All right, 2. So this is the moment of inertia beforehand. What do we have? Let's put our numbers in and see what we get. Justin doesn't already have the numbers. He must not be taking this example seriously. Let's see here. 0.5, 40. So this is 0.8. Seems kind of small. Plus 6.67-ish. Of course, that's kilogram meters squared, right? So you see the lion's share of the inertia in this situation is from the what? It's from the arms, right? And this, I mean, my choice of mass and physical dimension is a little bit ridiculous for a figure skater, but it's not completely far-fetched, right? A lot of the moment of inertia is coming from those outstretched arms, honestly. And so what's the final moment of inertia after it, when he tucks the arms in? So assuming he can tuck the arms really far in, I guess we shouldn't do that. So I should have what? I should have 1/2 the mass of the torso, r squared. And if the arms are as pictured as this, the arms are all aware. They're all at 0.2 meters, right? So what would the moment of inertia from that be? We do 0.2 meters squared times the mass of the arm. So 10 kilograms times 0.2 meters squared, yeah? So if your whole mass is at the same radius from the center of rotation, you just do mass times radius squared for inertia, right? So what's that give us? Still 0.8, right? I get 0.4, so 1.2 kilogram meters squared, right? So finally, getting to the point here, since, you know, in the moment that he just takes his arms or her arms and folds them in, there's no torque, right? Angular momentum is conserved, so before equals angular momentum after. Before, you've got the moment of inertia before times your initial angular velocity, and after, you got your moment of inertia afterwards times your final angular velocity, which means that omega f in this situation is going to be, what we got? Let's see here, 6.67 plus 0.8, which is 7.47 divided by 1.2 times omega naught, right? So what's that? Yeah, so we got 6.225 or 6.23-ish radians per second. And if you've ever watched figure skating, first of all, I'm sorry. But second of all, I'm sorry, it's a lovely sport. What am I talking about? Your relatives that are figure skaters? No? No? Do we have figure skating at Liberty? Yeah. Oh. Sorry, figure skating's great. Figure skating's wonderful. It's not a waste of your student fees at all. I'm sure it's not paid for by your student fees, which are not going up, I was told today. That's not unreasonable. So like the speed before they tuck their arms in is like, you know, it looks like it makes it 6 times faster. That's pretty neat, yeah.
Would it be 10 kilograms times 0.2 meters squared times 2? Because there's 2 arms.
Ah! Suppose, all right, so to not change the calculation. Oh, I can't do that. So the one arm, I'm going to have to change it to a robot. To change it to a robot, one of the arms is retractable into its core. So, but yeah, you're right. So, you got me. So that should be what? 1.4, well, no, wait a minute. 1.6? Rats. Yeah, that's not so easy to fix. I mean, I can't just add an explosion. See here. 7.47. 7.47 divided by 1.6. 4.67. So not quite as dramatic, but there you go. Anyway, so this is, I think these are pretty good examples. Another one I have, let me see if let me get out my projector here. Because I have some other examples I should talk to you guys about, but I've never really been successful at writing much more than about 3 examples in a physics class and explaining them. It's just the nature of word problems. All right, let's see here. Oh, I have so many things open. Ay, ay, ay. Well, we'll see if I can find my way back to the example. I'm not sure if the example I have in mind is in lecture 30 or if it's in lecture 28. I think it's worthwhile for us to go back to lecture 28 at this point because I think lecture 28 is actually using some of the ideas that we've just now developed. I mean, not entirely. Like this example. Where did I put my laser? Bah. Justin, did you take my laser? No. No. Funny if you did, though. Let's see, Katie? No. Sophie? Speaking of lasers, there we go. What's that? Oh, there you go. What's your last name mean? Light amplification by stimulated emission of radiation. Let's see here. All right, sorry. Ooh, well that one works. I thought I had a red laser. Where'd it go? Oh, it's in here. Whee! All right, so this has not so much to do with what we're talking about today, but it's worth mentioning again. Kinetic energy of a rod of length L rotating. So you do what? You figure out the net inertia, moment of inertia, and then that times omega I, 1/2 I omega squared gives you the kinetic energy. So there's another example of that for you. Let me get full screen here. Come on. This one is a kind of interesting example. Here I have a flywheel, and I have a hollow cylinder of inner radius 25 and outer radius 40, and I have it revved up to 30,000 revolutions per minute. It's kind of a lot. And then the question is, how far can you drive a car using this energy if it takes 10 kilowatts to maintain 40 miles per hour? I don't think that's unreasonable if you think about electric scooters, right? Like the best top-end electric scooter you can get is like 8,000 watts, something like that. How fast does it go? About 75 miles an hour. That's for one human, right? So 10 kilowatts for a car, 40 miles an hour. That seems kind of ballpark-ish, actually. So assuming 100% efficiency, because we've no other info, we have the kinetic energy is 1/2 I omega squared. The formula for the cylindrical shell is actually this. And so if you put in the numbers, you get 5.48 times 10 to the 7th joules, which is a lot. And so the flywheel basically serves as a sort of mechanical battery, right? And so let's see here. You've got power is change in energy over change in time. Your energy that we're talking about is up here. Your power consumption, 10 kilowatts, right? So 10 times 10 to the third. And that gives you 5,480 seconds, which is about 1.52 hours. So at 40 miles per hour, you got 60.9 miles if you had such a flywheel. And I should mention that there are 130 megajoules of energy in 1 gallon of gas, to give you a means of comparison. That is what? How many joules you got here? Let's see here. I think 55 megajoules. 55 megajoules in this huge flywheel, which is booking it, right? Versus double the energy for 1 gallon of gasoline. Like, I don't know. I don't think we appreciate enough how much energy there is in gasoline. Like, it's a lot. Anyway, so that was an example. Another example here. Find the final angular speed here for if you have a pendulum, right? And the pendulum is a rod of length L, and it just falls like that, right? So I can illustrate this. I can't because they cleaned the room. Curses. Anyone have a ruler? A large ruler? This is what happened when people pick up their stuff. All right, anyway. Oh, I know. So it's like this, right? I can't really do it, but if you could imagine me holding this, the question is how fast is what's the angular speed here of the bottom of the, how fast is it going in terms of, angles, radians per second as it crosses through the bottom there? You can figure this out using conservation of energy, right? Because you have what? You have the rotational energy of the ruler, right? And so 1/3 ml squared is the formula for moment of inertia. Energy is conserved so that I have the initial potential energy, which would be, well, let's see here. Well, I guess I'm saying the initial energy is 0. The final energy is, what do I got here? The kinetic energy plus the potential energy. Now, the potential energy, of course, is negative. If I take the original potential energy to be 0, I have net energy 0 before or afterwards. I have this negative potential energy being balanced by this positive kinetic energy, right? And so that gives you this formula right here. Now, notice this makes sense because YF is negative, all right? So where do you have to think about the mass being? You have to think about it being at the center of mass of the ruler. So YF is the halfway point on the ruler. That's where its center of mass is, assuming it's uniform density. This one will mess you up on a test or something if you haven't thought about it before. There's some things in here you got to really think through. So here you have, it's pretty much the same thing I was just doing. The question is, if you have a rod like this, let's say, right? And you've got it suspended by a pivot point here, right? Just as you let it go, right? Just as you let it go. What's the force on the pivot point, right? And what's the other question? What's the angular acceleration of the rod? Those are the two questions. So to answer these questions, you have to use Newton's law and you have to use, the rotational analog of Newton's law. So the torque, so we're talking about rotation around that axis. So the torque is given by gravity acting on the rod. So you can, basically, you think of the rod as a point mass at its center. That's where the torque you think about being applied, all right? And so the torque is going to be mg L over 2 because it's halfway. So the distance is L over 2 where we think about gravity being applied to the center of mass. And then we have torque is equal to I alpha. I here is 1/3 ml squared. It seems like everything is 1/3 ml squared in this today, right? It's the 1/3 ml squared day. And so anyway, the masses cancel and you get that the angular acceleration is actually 3g over 2L. So that's kind of neat. And a lot of times, if I don't have my head screwed on straight, I will get stuck on the question of what's the force at the pivot point. All right, so we have to think about Newton's second law there. The point is that Newton's second law applied to the rod is you've got minus the force at the pivot point, all right, and then the force of gravity, of course, and then the mass times the tangential acceleration. Now, for t equals to delta, which I'm saying is a really small but non-zero time, the centripetal acceleration is 0. It's not, see, it's still basically out. It's not this way. It's just this way, the motion. So we can write this equation right here and solve for FA. You get mg minus m, the tangential acceleration. But remember, tangential acceleration is the radius times is r times alpha. Here r is L over 2, alpha is that. And so what you get is 1/4 of the weight of the rod. So, and that's once it's let go. All right. If I'm holding both sides, you've got, I think, half of the weight here and half of the weight here, right? But when I let that go, it only takes a quarter of the weight to let it fall freely and to not let the rod move off the pivot point. So anyway, that's that. I have a couple more examples here, but I think I'm out of time, so I will stop here. Anyway, thanks guys.